Here's an example, a simple example of a mathematical model. Profit equals revenue minus expense. So that's mathematic, right? We can say it a different way. Profit is a function of revenue and expense. And here it is really in math form. Y is a function of x1 and x2. So that's a generic mathematical model where y is the dependent variable. It depends on the independent variable. So y, profit, is dependent on revenue and expenses. That's in our previous model. So most spreadsheet models, they're very similar to our generic mathematical model, and we actually create the mathematical model first before we implement the computer model. Here's three categories of models: prescriptive models, predictive models, descriptive models, and some examples. Predictive models, mainly in your statistics classes, you'll deal with those. Regression analysis, time series analysis, we probably won't do too much of that, but we'll do a lot of prescriptive models, which are where the independent variables are well known. Linear programming, network models, integer programming models, CPM, those are all fun things. We'll do that. And then descriptive models, simulation, PERT, we'll probably do some of those. And inventory models. Here's the problem-solving framework for leveraging business opportunities. So this is a problem-solving framework. These are the steps we go through. First, identify the problem. You've got to identify the problem and the correct problem before you start. It does no good if you build this wonderful model, but it's based on the wrong problem. It's a solution to the wrong problem. That's no good. We won't dwell that much on identifying the problem, but keep in mind that's extremely important. And a lot of times identifying the problem, it takes skills such people skills and communication skills and systems thinking and understanding of the business. All those are skills that are important with identifying the problem, and that's probably the most important step, I'd say. After you identify the correct problem, then you try and formulate it mathematically first and then implement it as a computer model. After that, we'll analyze it, test our results. This can be an iterative process until you get it right, and then we finally implement the solution. But it's this middle area that we'll be focusing on in this class. The psychology of decision making. Models can be used for structurable aspects. So basically, humans are not perfect. Humans are biased, and that's what it's talking about, the psychology of decision making. With the computer, we can model structured problems very easily, and semi-structured problems we can also model, not as easily, but very unstructured problems are very difficult to model, and they require intuition and judgment. So for instance, how much of this product or that product do we produce this month? That would be a very structured problem. We can easily model that, but should we build a new factory? That's a very unstructured problem. It requires a lot of intuition and judgment. It's hard to model that. So we can't model every decision. There's an art and a science to these decisions, and the unstructured problems, they're far more art, and the structured ones, we can make them less art, less questionable, if we model them. So that's what we're focused on. But humans, they're not perfect. We tend to be biased, and here's some examples of some biasness. This first one is the anchoring effect. You can read about that. Let me just show you their example. They gave people these two problems, and the problems are the exact same. It's just one of them starts with the smaller numbers and the other one starts with the bigger numbers. And what they found is people tend to, they said, hey, solve this real quick and don't use a calculator. The solution people came out with was much smaller for the problem that started with smaller numbers and ended with the bigger ones. So the one that started with bigger numbers, they would estimate, guess, or calculate the solution much higher. So interestingly, both of their solutions were way off. It just shows people aren't perfect and they make mistakes, and they tend to be biased. And this is the anchoring effect. we usually underadjust from the initial anchor, and the initial anchor in this case is a low number, or is it a high number? But the point is, trivial factors can affect how we think. The framing effect. This has to do with the win-loss perspective. Basically, people don't like to lose, and it depends on how you frame the problem. It can influence how people think and the choices they make. Media, politicians, they're very well aware of frame it in this way or that way, and it influences us and makes us have this opinion or that opinion. So you can think about politics or the media, and you probably understand what I'm talking about. But here in this example, suppose you've been given $1,000 and you have to choose between receive 500 more immediately. Well, that's positive. People tend to choose that choice over flip a coin and receive 1,000 more if heads or 0 more if tails occur. We like receive immediately. That's a positive thing. So people tend to choose that. Now, suppose you've been given $2,000 and you have to choose between give back $500 immediately, which would be the same $1,500 as the earlier choice A, or flip a coin and give back 0 if heads occurs, or give back 1,000 if tails occur. Well, give back $500 immediately is very negative, and it sounds like loss, and people don't like that. So in this case, they choose B. Although both of those, they have the same payoffs. Alternative A pays off $1,500, whether it was presented the first way or the second way, and alternative B, it's a 50-50 choice between 2,000 and 1,000. So same choices, but the way it was framed influenced how we made our decision. Now, the computer, when we model these computer models, the computer doesn't care. It's not influenced by these petty little human things. Final point here, good decisions versus good outcomes. A good decision doesn't always guarantee a good outcome. I've got an example here. This is off of Reddit. The woman made a great decision. Look at that on the top. That's what from the catalog. That's what she ordered. And no doubt about it, that's an awesome decision. That's a cool outfit. But the outcome, not so good. I mean, look at that. So the point is, a structured modeling approach, we can make our decisions more scientific, remove some of the artsy, wishy-washy aspects to it, that intuition and gut feeling. It can help us make better decisions, but it doesn't guarantee good outcomes. We're hoping that over the long haul, consistently better decision making will result in better outcomes, more profit, things like that. So decision quality, we can have good decisions with a good outcome. That's called deserved success. We can have good decisions with bad outcomes. That's just bad luck. Or we can have bad decisions that have good outcomes. That happens too. That's called dumb luck. And finally, bad decisions that have bad outcomes. Well, that's poetic justice. That's deserved. So that's the end of chapter 1. Next time we'll be doing chapter 2, and that's where we'll start with linear programming. So we want to look at doing it by hand first before we get into the computer, because the computer does a lot in the background and a lot of calculations in the background, and so we want to do some of those calculations by hand so we get an understanding of what's going on. Now, that'll be it for chapter 2 next week.